previous set of videos, we talked about permutations. And again, permutations need order. Combinations do not need order, which we'll talk about here. When we count permutations of n objects taken r at a time, we consider different orderings of the same r selected objects as being different permutations. In many applications, we're only interested in the ways to select the r objects, regardless of the order in which we arrange them. These unordered selections are called combinations of n objects taken r at a time. So the number of combinations of n objects taken r at a time is denoted NCR and is given by n factorial divided by r factorial times n minus r factorial, where r is between 0 and n. And again, if r is greater than n, then the combination is 0. Now also, you see that box right here? This means nothing at all. That box means absolutely nothing. That's the only way I can put it into Microsoft Word. Now we can verify the NCR formula with the multiplication principle. Since every permutation can be thought of as an unordered selection of r objects, followed by a particular ordering of the objects selected, the multiplication principle gives NPR is equal to NCR times r factorial, which means then that NCR will be the permutation divided by r factorial, which is 1 times r factorial, or 1 over r factorial times n factorial over n minus r factorial, which then in turn turns into n factorial divided by r factorial times n minus r factorial. So again, we are not ordering these. So in each of the following scenarios, tell whether permutations, which is ordered, or combinations, which is unordered, are being described. So a vice president, or a president, a vice president, and secretary chosen from a 25-member garden club. Well, in this case here, because there's 25 people, there's 25 people to choose from for president, then only 24 people to choose for vice president, and only 23 people to choose for secretary. That's why this would be a permutation, because order does matter. Now in letter B, a cook chooses 5 potatoes from a bag of 12 potatoes to make potato salad. So, does order really matter here? No, order doesn't matter here. It doesn't matter which potatoes you choose. So that, therefore, would be a combination. Now in part C, a teacher makes a seating chart for 22 students in a classroom with 30 desks. Well, obviously, here, order does matter, so that's why it'd be a permutation. Moving on to example 7. We're going to apply some combinations here by counting combinations. In the Miss America pageant, 51 contestants must be narrowed down to 10 finalists who will compete on national television. In how many ways possible can the 10 finalists be selected? Well, you have 51 contestants. We're going to choose 10. So that would be 51 factorial times 10 factorial times 51 minus 10 factorial. So you're going to take out your calculator. So this is going to be a big, big number. We don't want to have to deal with those. So I have 51 factorial divided by 10 factorial times 41 factorial. So we'll have 1.2777187 times e to the 10th. That's really going to be 12,777,711,870 ways to select that number. Now, a 3-woman committee is to be elected from a 25-member sorority. How many different committees can be selected? Well, again, that'll be 25, choose 3. So, how many different committees can be selected? So it's just a 3-woman committee, so there's really no order between president, vice president, secretary, so that's out. So we'll have 25 factorial over 3 factorial times 25 minus 3 factorial. So 2,300 different committees. Now again, you can do this a different way in your calculator instead of using all the factorial symbols. You could say 25, choose 3, and you get the same number. So you can do that right in your calculator to make it much, much easier for yourself. Now looking at example 8, the Georgia Lotto requires winners to pick 6 integers between 1 and 46. The order in which you select them does not matter. Indeed, the lottery tickets are always printed with the numbers in ascending order. How many different lottery tickets are possible? So there's 46 numbers. We're going to choose 6 of them. So here's what we're going to have. 46 choose 6. 9,366,819 tickets. Now in letter B, it says Juan has money to buy only 3 of the 48 compact discs available. How many different sets of discs can he purchase? So then, 48, choose 3. So you can have 17,296 different options. As a final application of counting principle, consider the pizza topping problem. Now, Armando's Pizzeria offers patrons any combination of up to 10 toppings. How many different pizzas can be ordered if we can only choose any 3 toppings? So we have 10 different toppings, but we're only going to choose 3. So how many different toppings or how many different pizzas can we create? So what we're going to do, we're going to do 10 choose 3. 10 choose 3 is 120 different pizzas. So really what we're doing there, you're saying, well, I've got 10 options. So yes to pepperoni, yes to mushroom, yes to sausage, but no to every other topping. And there's going to be 120 different options for that. So really, because there's only 2 options, either yes or no for all these, if we can choose any number of toppings, 0 through 10, what we're going to be able to do, there's 2 options for pepperoni, 2 options for mushroom, 2 options for sausage, 2 options for onion, 2 options for green pepper, 2 for bacon, 2 for prosciutto, 2 for black olive, 2 for green olive, and 2 for anchovies. So if you do this, it's really going to be 2 to the 10th power. 2 to the 10th power is 1,024 different options. Now, the solution to example 9b suggests a general rule that we are last counting formula of this section. There are 2 to the n subsets of a set with n objects, including the empty set and the entire set. Now, if we look at example 10, a national hamburger chain used to advertise that it fixed its hamburgers 256 ways, since patrons could order whatever toppings they wanted. How many toppings must have been available? So really what we're going to do then, we're going to have 2 to the n power is equal to 256. Now to solve this, we're going to take the log of both sides. We're going to use a property of logarithms to bring this down. Which means n will equal the log of 256 over the log of 2. So in your calculator, you get the answer there of 8. So there's 8 different toppings that the national hamburger chain would offer. Now, if we look at letter B here, Luigi sells one size of pizza, but he claims that his selection of toppings allows for more than 4,000 different choices. What's the smallest number of toppings Luigi could offer? So what we're going to have then says more than 4,000 different choices. That means 2 to the n has to be greater than 4,000. Again, we're going to do a lot of the mathematics here. So n log of 2 is greater than log of 4,000. That means n has to be greater than the log of 4,000 divided by the log of 2. That's be about 11.97. So n will equal 12 toppings. And there you have it.